right, so now that we've finished our nomenclature of alkanes, we're going to talk some more about where we find them, what they're useful for, and so on. So one thing we might wonder is, where do we find alkanes? And so the primary place that we find alkanes is as petroleum. So when you hear that term petroleum, what we're really talking about is a substance that's a mixture of many different alkanes. And we can separate those alkanes on the basis of boiling points. So how is it that we're able to do that? And why? And what do we find in those different ranges? So at the low end, lowest boiling point, lower than 20 degrees, very small number of carbons, 1 to 4 carbons. We find a lot of hydrocarbons that are used both as fuels and or for making plastics. So as we'll learn about later, especially when we get into the chapter on alkanes, many fuels, most fuels, are hydrocarbons, and plastics are generally polymers where we string thousands and thousands of carbon molecules together. As our boiling point goes up, so does our number of carbons. We also find a lot of fuels, or gas for our car in this range, and we find a lot of common solvents. Going slightly higher, that gets us about 12 to 16 carbons. Here we find our diesel fuel, as well as a lot of hydrocarbons that we use for a process known as cracking. So cracking is a process where we take hydrocarbons and break them apart into lots of smaller hydrocarbons that we can then use for other purposes. Going up a little bit more, again, in this range, these are used for cracking, but you may also see these used as heating oil. And then sort of in the highest range, where we get them to boil easily, above 350 Celsius, 16 to 20 carbons, and a lot of these are used as lubricants. Now that doesn't mean we're done, because there is stuff that's even higher boiling. And really won't boil easily. So we just refer to that as the leftover residue. Generally, these are compounds containing more than 20 carbons. Most common use is that's how we make asphalt, is from that leftover residue. So why is it that we're able to separate these on the basis of boiling points? Well, this is something you may remember from general chemistry or foundations. But all of this, in terms of boiling points, is based on intermolecular forces. So remember that intermolecular forces are the forces between molecules. These are not actually bonds. These are the forces between molecules. And so in Gen Chem or Foundations, we probably went over a whole bunch of different types. In this class, we're going to focus on the ones that matter to organic molecules the most. Dipole-dipole, the very unfortunately named hydrogen bonding, and the van der Waals forces. So we're just going to take a few minutes and review these. This should all be reviewed from previous course. But what is dipole-dipole interaction? Well, we know that anytime we have a molecule where the electrons are not shared equally, one with a polar covalent bond, those electrons go in the direction of the more electronegative atom. And that can kind of look like this. The delta plus refers to not a full positive charge, but a partial positive, and a partial negative where the chlorine is. Then if another molecule comes along, its positive end will be attracted to the negative end of the other, and we form an attraction between these neutral but still polar molecules. Now, this is nowhere near as strong as a bond, and nowhere near as strong if we had ionic intermolecular forces. But when we think about organic molecules, they're almost always just these polar covalent molecules. And so dipole-dipole is the strongest attraction we see for the overwhelming majority of molecules. Now, hopefully you also recall hydrogen bonding. Now, we want to be careful and remember, because this is one of those very, very poorly named ideas, because it's not actually a bond. It's another intermolecular force. And specifically, it's a special case of dipole-dipole. This is a hydrogen on a nitrogen, oxygen, or fluorine with a nitrogen, oxygen, or fluorine. So if we have an alcohol, for example, we get an attraction between the oxygen on one alcohol and the hydrogen that's on the oxygen in another molecule. And these hydrogen bonds are a large part of the reason why molecules such as water has such a high melting point, such a high boiling point compared to other similarly sized molecules. Now, these types of intermolecular forces, such as hydrogen bonding, are also extremely crucial biologically. And that squiggly line coming off the nitrogen, all I mean there is the molecule keeps going. So we have these two molecules here. And when they line up, this oxygen up here at the top can form a hydrogen bond with the hydrogens on this nitrogen. This nitrogen here lines up to form a hydrogen bond with the H on the nitrogen. And we get a third hydrogen bond between these two molecules down here at the bottom. So what are these and why do they matter? Well, on the left we have guanine, and on the right is cytosine. These are two of the base pairs we find in DNA. And we could draw a similar set of hydrogen bonds for the other base pairs of adenine and thymine. But sort of very simply, that if these hydrogen bonds didn't exist, then the entire double helix of DNA would just fall apart. These types of intermolecular forces we'll also see again for those who are going to take biochemistry, because these intermolecular forces are what keep proteins together. And we don't mean the structure, the sequence of the amino acids, but we mean the shape of the proteins, which oftentimes has just as much to do with the function as which amino acids you have. Right. The other IM force that we want to review briefly are what we call London dispersion forces. These are also sometimes known as van der Waals forces. And these are, without any doubt, the weakest intermolecular force that we have. And that's because these are what occur in nonpolar molecules, such as a hydrocarbon. So here's propane. Carbon and hydrogen, though, are of extremely similar electronegativities. And so because of that, there are no polar bonds. But what happens is that electrons are always in motion. And they're pretty much randomly distributed throughout the molecule. But there might be some point where more of them are on one side of the molecule than the other. And that's what we're picturing here. And so in this case, we end up with a temporary dipole. And we say that it's temporary because as soon as the electrons start moving again, it can just as easily go away. At the same time, if there's another molecule nearby, it could induce a dipole in that molecule. And so we start to get some weak attraction. All right. So what does this all have to do with melting points, boiling points of molecules? Well, the melting point or boiling point of a compound is controlled by how strongly the molecules are attracted to each other. Or in other words, how strong the intermolecular forces are. So the stronger that attraction is, the higher the melting point or the boiling point. And so that's why small molecules like methane which have only van der Waals forces and are very small, have very weak attraction. And so if you want, can you make methane a solid? Sure. You're just going to have to get it below negative 182 degrees Celsius. And it even boils at negative 164 Celsius. But when we go to a larger molecule, such as pentane, now the melting point goes up to negative 130 Celsius, and the boiling point actually gets to a point that it's a liquid at room temperature. So why the difference? Well, larger molecule leads us to more surface area, which gives us more opportunity for London forces. And so the more opportunity we have for London forces, the stronger the attraction. So in general, higher mass, higher melting point and boiling point. And so if we go up to 10 carbons, which is decane, the melting point now is all the way up to negative 30 degrees Celsius. And the boiling point is actually much higher than water, 174 degrees. And eventually, if you put enough carbons together, say 40 of them, just in a straight chain, you do eventually get a strong enough interaction that you'll get a hydrocarbon that's actually solid at room temperature. Now, all of these are straight chains. What happens if the molecule branches? Well, let's look at a bunch of isomers, all with formula C6H14. Well, again, with London forces, what controls the attraction is how much these molecules are able to interact. So the more surface area you get, the better the attraction. Less branching means the molecules pack together better. And so when we have no branching at all, we just have 6 carbons in a straight chain. And these are all boiling points that I'm going to put down. 68.7 degrees Celsius. As soon as we start to branch these, we make them, they don't pack as well. And so the boiling points start to go down. The more branching, the worse the packing of these molecules. And again, the lower the boiling point. So that's the first thing we want to consider. With intermolecular forces. And we're going to come back to this with each functional group. The second thing to consider that intermolecular forces play a big role in, solubility. And in general, we're just going to concern ourselves with solubility in water. So what do we think? Are alkanes soluble in water? Well, alkanes, which contain only van der Waals forces, are highly nonpolar. Water, on the other hand, with hydrogen bonding, is very polar. So will they be soluble? Answer is no. In general, solubility is determined by polarity. If you want two molecules to be soluble, then their polarity needs to be similar. Or we often say like dissolves like. So a polar solute will dissolve in a polar solvent. A nonpolar solute will dissolve in a nonpolar solvent. But nonpolar and polar in general won't mix. All right, the final thing we want to say in this chapter is what can we do with an alkane? What reactions will they do? And the simple answer is not much. Alkanes are relatively unreactive. Now, in many ways, the most important reaction of alkanes, and we use them as fuels, and that's that we can burn them. So combustion, you add oxygen to an alkane, and the result is some amount of carbon dioxide and water. And most importantly, energy. So regardless of what alkane you're burning, the products are going to be carbon dioxide and water and energy. And that's why we're able to use them as fuels. The other reaction we see for alkanes is halogenation. And that's that you can take an alkane, such as methane, and add a halogen to it. And then you expose it to UV light. And it forms, one of the hydrogens gets replaced with a halogen. Now, the main problem with this reaction is it can keep going. It's actually very difficult to control. And so you often end up with a mixture of all the different products. But in some cases, you can control it and can control it extremely well. And it can become a very useful reaction. And why would we want alkyl halides? Well, alkyl halides have a lot of use in labs as solvents. They've been used for many years as refrigerants, chlorofluorocarbons. And then in the lab, once we've made an alkyl halide, we can easily convert that into a lot of other different functional groups.